Hi everybody, and welcome to example 1. We are looking at page 14 of the workbook, and in this video we're actually going to be working through examples 1 and 2, kind of compare them to each other. Okay, so let's read example 1 together. It's telling us that the temperature on a 6 meter by 6 meter metal plate at the point xy is given by the formula T of xy equals x squared plus y squared degrees Celsius. They'd like us to discuss the significance of the objects that we see below. Okay, and let's start with the picture to the left here. What we're really looking at here is the graph of the function t. Okay, it's just a three-dimensional plot that gives us a plot of the two inputs, x and y, and gives us outputs, temperatures, on the vertical axis. Okay, so for example, if we took the point x equals 2 and y equals 2, okay, so x equals 2, then over to y equals 2, and we go straight up to the surface, we would have a point on this surface that looks like 2, 2, and if we plug those 2's in, we're going to get 2 squared plus 2 squared is 8. Okay, which is a way of saying that if we're at the point x equals 2 and y equals 2 on this plate, we're going to have a temperature of 8 degrees Celsius. Okay. What do we have over here to the right? Well, this is what we called either a contour plot or the level curves of our function. Okay, kind of remember what this means. So these numbers that you see, the 1, 4, and the 7, here, here, and here, those are temperatures. Okay, so for example, if we just pick on one of those, the 4 that we have here, that circle that's labeled with a 4 is just telling you all the positions on the metal plate where we're having a temperature of 4 degrees Celsius. Okay, these are two different ways of representing the same function, and the thing that I'd like you to notice about this is the difference in dimensions. The graph over here is in 3 dimensions, whereas the level curves are in 2 dimensions. I'm going to write that down. Okay, so a contour plot is a way of taking a 3-dimensional graph and breaking it down into a 2-dimensional representation. Okay, that's example 1. So let's move on to the next page. See how this example is different. Okay, so in example 2, a block of ice is located at the point 0, 0, 0 in 3-dimensional space, and the temperature at the point xyz is given by T of xyz equals a fourth times x squared plus y squared plus z squared. Okay, so first question that they ask us is, how many dimensions would be required to represent the graph of t, this function that they gave us? Okay, well, you might be tempted to say 3 because you see x, y, and z, that's 3 variables. But actually, to draw a graph, you would need 4 dimensions because not only do you have x, y, and z, the 3 input variables, but you have an output variable of t. Okay, so you would need 4 dimensions in this case. Okay, so 3 for x, y, and z. And 1 for t. So trying to draw a graph of this function, that's not something we can really do because our universe kind of takes place in 3 dimensions. We can't picture a function of 4 dimensions. All right, and so what we can do to analyze a function like this is to take one of the variables and set it equal to a constant. That's kind of what's going on down here. So we've got 3 surfaces that we get by taking the temperature and setting it equal to a specific value, T of xyz equals 1. The claim here is that we get a surface in 3-dimensional space if we do that. Okay, and they'd like us to, one by one, find formulas for those 3 surfaces and then to explain their significance in this problem. Let's do that together, starting with the first one here. So T of xyz equals 1. Okay, so if we do that, we're literally just taking the formula for t, which is sitting up here, and setting it equal to 1. All right, let's play with this formula. We can multiply both sides by 4 to get rid of that 1/4. And the question is, what are we looking at? X squared plus y squared plus z squared equals 4. What is that the graph of? Well, if you go back to the previous page, that's the graph of a sphere. Its radius is 2 because 4 is 2 squared. Okay, sphere of radius 2 centered at the origin. Okay, and what's special about that sphere? What's its significance in this problem? Well, one way to think of it is to remember that this 1, that's a number that we set equal to t, x, y, and z, so that means that that's a temperature. So you can think of the sphere as being the set of all points in three-dimensional space where the temperature is 1 degree Celsius. Okay, so we're sitting at a particular distance away from the ice block that's at the origin, and this is just telling us that we're getting a temperature of 1 degree Celsius at every point on this sphere. Okay, and let's move on and do the other ones. So t of x, y, z equals 5. Very similar calculation, just that we're setting our temperature equation equal to 5 in this case. Okay, we'll do what we did before, multiply both sides by 4, and what we wind up with is x squared plus y squared plus z squared equals 20. That's also a sphere. What is the radius of the sphere? Well, it needs to be a number whose square equals 20, so the radius is going to be the square root of 20 in this case. And this time we'd be talking about the points in space where the temperature is 5 degrees Celsius. Okay, it's a little bit warmer on this sphere because we're a little bit farther away from the ice block that's at the origin. Okay, and then finally, last calculation, same idea. Okay, if we take our temperature, set it equal to 9, and kind of do the algebra here, this time we're going to get a 36 when we multiply both sides by 4. So here we're looking at a sphere of radius 6. Okay, and this is points where the temperature is 9 degrees Celsius. Okay, and one last thing we might do on this problem is to go back up and see if we can, they gave us a picture and said that this picture contains 3 surfaces and each surface matches one of our formulas. Okay, and looking at the relative radii, the size of these things, we can see that the smallest sphere, that must be the 1 that goes with a temperature of 1, and then the one in the middle is a temperature of 5. And then the very biggest sphere on the outside, that's going to go with a temperature of 9. Okay, and so finally, just to sum up this discussion, these surfaces that we just found in part B have a special name. They're called level surfaces of a function. Okay, and that relates to this definition that we're seeing down here. So if you start with a function of 3 input variables, w equals f of x, y, and z, its graph would occur in 4 dimensions, so we can't draw its graph, but we can do what we did in part B above. We can analyze its level surfaces, and you get a level surface by just setting the output variable equal to a constant. Okay, and then asking, what does that 3-dimensional surface look like? Okay, it just tells you all the points in 3-dimensional space where the output value of your function is constant and equals c. Okay, in the rest of the section, we will explore this idea of level surfaces.